There we go. Alrighty. Hey, guys, I apologize for being a minute late here. I was just coming out of office hours. I have students who are strenuously objecting to learning the change of variable theorem for multivariable calculus. It's just not sitting well for them, and I don't know how to help them. I think they're just at their limit. If any of you guys has a suggestion for how to explain the change from polar coordinates into rectangular coordinates, I mean, which side is being changed into which one, that seems to be the stumbling block for my students. Anyway, how are you guys doing? Hey, listen, I gave you some homework questions to try. I've spoken to a couple of students about there's a computational one where I asked you to show that a number is composite, and the thinking was that you would use Fermat's little theorem, or more precisely the converse to Fermat's little theorem. There's nothing wrong with the way that I phrased it before. I was trying to give you a hint that this idea of repeated squaring can take you pretty far into the chain of powers very quickly. But even at that, when you do all the computations just by hand or just with a hand calculator, it takes a little long. So I changed the questions. I don't know if you guys have seen them. I think I can share my screen. Yeah. Here, you're certainly welcome to pursue part A as I phrased it originally, but using these numbers can make things go a little bit faster. I've replaced the composite number at the top, this 2047. I've given you a smaller one, so that makes life a little bit easier. And with some experimentation, I discovered a number, this 47 here, that turns out, for no particular reason, to work better when you're working modulo this composite number than, let's say, 3 would. So there's nothing wrong with using the number 3. It's just that you have to work a little harder. There's more computation to do, perhaps surprisingly. Using the slightly smaller number 47 instead of a 3, you'll see a pattern a little sooner. That's the advantage to that one. So, like I say, there's nothing wrong with the question A as it was originally posed, but you might find it more useful if you have the capacity of, I don't know, just get a Excel spreadsheet going or something so that you could do the computations a little more rapidly for the number 2047. Maybe it takes a little too long just to do it by hand. All right. Anything else that we should clarify, like on the homework or the material from the previous sessions? All right. Listen, we've been pursuing a lot of things with powers, and I've hinted that this has some connection with primality testing, and I've had a couple of people ask me for more details. I can give additional homework exercises, I haven't written them down yet, that talk about that issue. But I'm going to go in a slightly different issue and finally start to get to this cryptography application that I've mentioned since the beginning of the semester. We're at a position now where we can start to talk about it. And precisely what I'm going to describe to you is what's known as the RSA encryption technique. So it's named after the 3 mathematicians that set it up in the first place. It works pretty well. In fact, if you use this encryption technique that it's like when you go to a website and it says HTTPS, it's supposed to be making a secure connection, and it uses this thing called pretty good privacy, PGP, and it's based on exactly this encryption technique, and that's the one I'd like to illustrate with you guys today. So we're going to use Euler's theorem for powers modulo a composite number. So let me spin this around here. And oops, how do I get it lined up? All right. So here's the thing. So suppose that you want to transmit a message to somebody and you want to make it encrypted so that somebody who's eavesdropping can't tell what you're saying. I don't know exactly what kind of a message you're trying to send to the other person, but for our purposes, it'll be sufficient to assume that it's just written out with the letters of the English alphabet and the ordinary English pronunciation, punctuation rather. So your message might be something like this. You might decide to say, we can have upper and lower case, you'll see. Math is fun. There. So there's my message. Okay, there are a lot of ways that you can hope to encrypt this. And when I say encrypt it, I have in mind that we want to encrypt it for privacy, but there are other times that you just want to, I don't know, you want to have a different way of sending this. So then maybe the better word is encode instead of encrypt. So for example, if you want to send something in a typical computer setting, then you want to write everything as a sequence of zeros and ones. And there's various ways of doing this. So you guys probably know about things called Unicode, or the older predecessor of that was called ASCII. These are mechanisms that change any sequence of letters into a sequence of zeros and ones. Specifically, all of these things can be changed into numbers between, in case of ASCII, you can change them all into a number between 0 and 127. So if memory serves me correctly, for example, a lowercase a is represented as the number 33. It's because the numbers from 0 up to 32 are used for other things besides letters. And then this is the first letter of the alphabet, so it's a 33. The letter B would be the number 34, and so on. I don't actually remember what all the other letters are, but at some point you switch to uppercase by adding, I think it's a 64. So the letter capital A would be written as, I believe it's a 33 plus 64 would be 97, etc. I don't have the ASCII conversion table memorized, but I will tell you that each of these things could be written as a single number that's in the range of 0 to 128, 127. And like I said, there's a few of these, there's only 26 letters in the alphabet, so even with upper and lower case, even including spaces and other punctuation, you need far fewer than 128 combinations. So for our purposes, we can delete a few of the entries that are in the ASCII code and just replace every one of these letters by some number that's in the range of 0 up to 119. I just need 120 different characters altogether. So every message that you write can be written as a sequence of 120 different characters. Now, there's a reason that I chose the number 120. ASCII actually uses the numbers from 0 up to 127. That's a power of 2. That's a more natural thing in computer land. But for us, at this moment in our number theory class, I wanted to know that this is 120 different characters, 120 different symbols that I might be using in any message. And my idea for encrypting these is to take every one of these characters in this range and to change it into a different character in the same range. I want to have a function f that just replaces every one of these numbers by a new number that's one of these 120 possibilities. Here, I should write it as not an interval, it's a set that has this 120 different possibilities in it. So that's where I'm going to focus. That's where the number theory is going to come in. I'm going to talk about how to get some functions that replace every one of these numbers by a different number. So this is really just an encoding question because my numbers are so small. If you really want to do encryption, the way people work this is they take a string of characters and we string together all the zeros and ones that are in the ASCII coding. And then instead of having, let's say, numbers that go from 1 to 128, instead of having, what would that be, 2 to the 7th different combinations, because these are strings of 7 zeros and ones, as soon as you put 4 of these things together, well, that's a string of 28 zeros and ones. And so now you have a set of numbers that's in a range of 2 to the 28th combinations. So you're going to see me deal with numbers that go up through the range of about 2 to the 7th power. And I'll be doing some arithmetic with numbers that are that small I can kind of do them by hand, or I'll pull up my computer when it's necessary to get slightly bigger numbers. But if you want to make your codes a little more secure, make it more difficult for an eavesdropper to crack the code, then you would want to use bigger strings of zeros and ones besides just 7 of them at a time. The current recipe for good security is they suggest that you use, I think, 1024 bits at a time. In other words, you would be talking about numbers that are 1024 bits long. So those translate in base 10, those would be like 300 and some odd digit numbers. So be thankful that I'm just dealing with 3-digit numbers here. But in a real secure situation, you would have hundreds of digits at a time. You'd be doing a lot of reductions mod n, where n is a number with hundreds and hundreds of digits. All right, now why am I repeating this business about 120 so much? The number 120 comes because of this piece of information that we had before. We have been working with the Euler phi function. And when I asked you to compute the Euler phi function for the number 143, well, the way to do that is to know the prime factorization of 143, namely it's 11 times 13. And so my recipe for computing the Euler phi function is that it's the same 143 times these factors of 1 minus 1 over 11 and 1 minus 1 over 13. And when you multiply each of those funny fractions times the corresponding prime, of course, then you're getting the exact numerators, excuse me, the exact exponents that show up in the Fermat theorem, which are 10 and 12. So those were the Fermat theorem when you work mod 11 or mod 13, because each of those is a prime number. The number 143 is not prime, but we still have Euler's theorem. So here's Euler's theorem at work now. And Euler's was the statement that A, in our particular case for the modulus 143, it tells us that A to the 120th power will be congruent to 1 modulo 143. And of course, you do have to make a restriction on that. You need to know that A is co-prime to 143. And here's the way that I phrased this for you last time. I said that this would be true for all A's that are in this group, this collection of congruence classes modulo 143, which are invertible. And I had a little digression with you last time to observe that I know exactly how many elements that there are in here. The size of this set is exactly phi of 143, which is again that number 120. So this is why I wanted to use not the full set of ASCII characters, but I want to use just a restriction of them. I want you to use at most 120 different symbols, because the way I'm going to have this message get encoded is I want you to take every letter and convert it to one of my 120, and then match those 120 symbols with the 120 elements of this set. So here's my first step of my encoding algorithm. And you do that by exchanging for representing each of my up to 120 characters as an element of this set, Z mod 143 cross. And I don't care how you do that, but we should just all agree on some mechanism that would let us do that. And when I say we should all agree, I mean I, who am trying to send the message, and you who are going to receive the message. And honestly, I'll even allow any eavesdropper to know the encoding method that turns every bunch of letters into a bunch of elements in this, it's actually a group in this ZMod 143 cross. So we might agree, for example, that I'm going to send the number A, the letter A goes to the number 1, B will go to the number 2, C goes to 3, D, E, F, well, 4, 5, 6, 7, 8, 9, 10. Now I have to skip the number 11. In other words, the congruence class of 11 modulo 143. It's not an invertible congruence class because that obviously divides 143. So the next number that I will choose will be 12, and I can use that for K. The letter K will be sent to the number 12. Well, here, L, M. So there's a 13 and there's a 14. N, O, P, Q, R, R, S, T. Oh, sorry, I can't use the number 13. Sorry?
I was going to say the same thing. We should skip 13.
Yes, thank you. I got ahead of myself. I need to skip all the multiples of 11 and all the multiples of 13. Those are precisely the 23 elements that have to be excluded. There's 11 multiples of 11 and there's 13 multiples of 13. I'm sorry, I said that backwards. There's 13 multiples of 11 and 11 multiples of 13. And then there's one number that's a multiple of both 11 and 13. So 143 minus 11 minus 13 plus 1. There's inclusion, exclusion for you.
Why don't you start with 0? Why do you start with 1?
Doesn't matter. Oh, no, I can't use 0. I need an invertible element of 143. When I say integer, I should, let's be clear. These are all going to be turned into congruence classes modulo 143. So when you ask me to start with the number 0, hey, by the way, you must be like a C programmer or something. Most people don't start counting with 0. They can't. In fact, I'll just tell you guys, I had a Zoom meeting yesterday with, I sing in a chorus, and now we can't sing together because, you know, nobody's supposed to get together. So we were talking about music theory, and we were talking about intervals. And so there is an interval on a piano, it's called a fifth. But that interval is it's called a fifth because it involves two notes, two keys on a piano that are 4 apart from each other. For historical reasons, it's called a fifth because you count all the notes that are in the chord, in the interval, including the spaces in the middle, and you start counting with 1, 1, 2, 3, 4, 5. But it gets very confusing because if you put 2 fifths together, you don't go up to a 10th, you only go up to a 9th. If they had been clever in the first place, they would have started counting with 0 and that interval would have been called a fourth. But anyway, that's history. So I can't use 0 anyway because I need invertible elements of Z mod 143. But that's why I skipped the 11 and I need to skip the 13 as well. So 14 would be next, 15, 16, 17, 18, 19, 20, 21, and I can't use the 22 either because that's a multiple of 11. So the number T is going to have to be a 23. And I went out that far so that I can show you that my message that begins by saying, I'm switching to lowercase now so I can read off my table, math is fun, is going to turn into a string of elements of this group. So M was the first, and then A was the next, T was next, and then H was next. And at some point in my list of all these characters that I might want to send, I might want to include the uppercase letters and the space and the punctuation and everything else. So I don't know what number would be assigned to the space. You know, here, I'll make that be 142. How's that? Okay, so the point of this first step is to say, yes, I understand that your messages are usually expressed in a human language, which is done with a human character set. Even if you're using Chinese, there's Unicode encryption or encoding of all of their characters. So ultimately, your message becomes a string, not of individual characters, but of elements of, for us, it's going to be Z mod 143 cross, but you could replace this with some enormous integer n. It could be way bigger than the number of characters, even though if I just wanted to use the letters of the English language, there's nothing from stopping me from using a 1,000-digit composite number for capital N. I would just have to make this table that shows exactly which elements of Z mod n I want you to associate with each letter. Okay? And I will just say, in case some of you are actually thinking of writing secret codes, you probably want to use a big number n, because somebody who stares at this table would say, oh, look, they skipped over the number 11. 11 must not be co-prime to the modulus. And so you're giving somebody some information by having all these densely packed numbers and then skipping over something. That sticks out like a sore thumb. So in the spy business, you don't want to do anything that looks glaringly obvious. That always, anytime you do that, you're giving the opposing team some information that they will use. But I'm going to assume that any eavesdropper is stupid. So I'm going to just restrict to numbers that are between 1 and 142. And there's the beginning of my message. Now, here's how the RSA encryption technique works. To encrypt a message, what I'm going to do is I'm going to say replace each one of these integers alpha. And by the way, I deliberately wanted to use something that's not an ordinary Latin letter because I didn't want you to think that that was part of a message. So this is obviously not a Latin, but it's a math variable here. And replace any one of those integers mod 143 by alpha to the 7th power. And of course, when I say that, I want you to take its 7th power modulo 143. So you're still continuing to do the calculations in this setting. Now you know that it will still be an invertible element modulo 143. In fact, it's even easy to see why this number is going to be invertible, because it's the product of 7 invertible elements. If the inverse of alpha is beta, then the inverse of alpha to the 7th will be beta to the 7th power. So for sure, this is another invertible element. All right, well, so this will turn my message into, that's all it is. That's all you do to encrypt, is you replace every single one of these integers, mod 143, by a different integer modulo 143. So the encrypted message now looks like this. It's going to be, see, where was my message? Oh, here it is. 15, 1, 23, etc. So it's 15 to the 7th power modulo 143. And then it's, well, 1 to the 7th power modulo 143. Of course, I already know that one's going to be just a 1. And then I need 23 to the 7th power, etc. Oops, yeah. So however long my original message was, this will be another message of the same length, but all of the numbers will be scrambled. All right, so now let me actually have a machine do the calculations for me. I'll share my screen in a second. Okay, how do I do the share screen? Here it is, like this. Okay, so my message is going to be, what did we say? Here's the first few parts of it: 15, 1, 23, 8, and 142. So that's going to, we know that that's just 5 characters. And if we have the table in front of us, we can read from the bottom line to the top line to change each of those numbers back into a letter. But I'm going to encrypt this by taking each, it's going to be a sequence of encrypted characters. All I'm going to do is to take each one of these alphas and raise it to the 7th power modulo 143. And I'll do that for each alpha that's a member of this thing called message. Unfortunately, Maple doesn't have a character that looks like the element symbol. They just use an equal symbol, which I know is kind of confusing. But there we go. There's our encrypted message. Now, one of those numbers you kind of expected already. We knew that if you took the number 1 and you raised it to any exponent, of course, you're just going to get a 1 back. This is perhaps a little surprising, but the number 23 also has that feature. When you take 23 to the 7th power, you get 23. That must mean that, well, if this statement is true, then if I divide both sides by 23, which is to say multiply both sides by 23, then, so by the inverse of 23, that must be telling me that 23 to the 6th power must be congruent to 1 modulo 143. And sure enough, that's what Maple reports. Okay, well, it is what it is. So that's my encryption, is that I got an encrypted version of the original symbol. The fact that 142 also had that same feature, that one you could have predicted, because if you're working modulo 143, then 142 is congruent to -1. And obviously, if you raise -1 to the 7th power, I don't have to reduce modulo 143. Obviously, that is just equal to -1. Okay, now, an encrypted message can be kind of mysterious, but it's not helpful if your message is so mysterious that there's no way to decrypt it. So I have to figure out now a way for my correspondent to receive the encrypted message and figure out a way to decrypt that one. So here's the trick. To decrypt, my recipient has to be able to take each one of these letters, well, the numbers alpha, which I have already raised it to the 7th power, and somehow have some sort of a function that takes this thing and creates the number alpha back. I want to somehow get my original character, one character at a time, by taking the 7th power of alpha and using the 7th power of alpha to figure out what alpha is. In other words, what I need is for f of an input, I don't want to use Latin letters today, f of any input, that's a gamma, should be the 7th root of gamma. But I don't know how to extract roots, modulo 143. And besides, we could run into all kinds of problems. We've already just discovered that when you want to look at the 6th root of 1, well, we found that that could be a 1 or a -1, or it could be 23 as well. And who knows, maybe there's other possibilities. So extracting roots doesn't seem to be a useful thing to do in modular arithmetic. But you know what? It turns out it does work, at least sometimes. Extracting a 6th root is problematic, but extracting a 7th root is not. And I'll show you why. Because another way to write the 7th root function is to say that, in some sense, what I'm looking for is I want to take this, I want to take whatever my input is. What f should do to a typical input is I should raise it to the 1/7 power. Well, that doesn't feel any different from what I had previously, but it does give this idea that maybe what we want to do is to have our decryption method is to be a function that takes an input and it raises it to some kind of exponent, e, that has the feature that e plays the same role as the number 1/7, at least as far as exponentiation is concerned. Now that's the useful idea, and it ties into Euler's method, Euler's theorem rather. So somehow we need an e that, now's where the word somehow should be applied. It works like 1/7 in an exponent. Well, that's really faint. You know what? I have a marker. My markers are running a little dry. That's why I stopped using it. But I want to somehow make E to somehow resemble the number 1/7, but only in exponents. There, is that easier to read? But here's what I'm thinking. Since we're only working mod 143 in the first place, we've already mentioned Euler's theorem that tells us that if you take any one of these numbers, alpha, and raise it to the 120th power, then that will just give you a 1 back. In other words, that's acting like alpha to the 0 power. Multiples of 120 act as if they are nothing. So what you want to do is to say, well, I need to figure out something that how do I get you to anticipate what I'm about to write down without just writing it down? Oh, here, let me say it this way. When you say that E needs to behave like a 1/7, in some sense what you're saying is that you need E times 7 to act like a 1 somehow. I'm being pretty informal, pretty vague, but that's trying to set you up is to say, wait a minute, taking something to the 120th power took me back to 1. In other words, taking something to the 0th power. If I'd have gone 1 more power of alpha, that would have been, I should say congruent, that would have been congruent to alpha to the 1st power. So here, the number 121 acts like a 1 as far as exponents go. And there's nothing special about the 120 except for the fact that it is 1 more than the number 120. In other words, I could have equally well used 240. That would be alpha to the 240 power, excuse me, alpha to the 241st power would be congruent to alpha to the 1st power, and so on, taking any alpha to the 120 times k. Oops, I said I wasn't going to use Latin letters. Give me another Greek letter that doesn't look like a Latin letter. Delta. I was going to change it to a kappa, but that looks too close to k. Any exponent of this form, put on any of these numbers alpha, any of the 120 elements alpha, you will get alpha back if you raise it to an exponent, which is 1 more than a multiple of 120. So what I'm asking for here is what I really need.
Where is the 120 coming from?
120 is right here. That's in Euler's theorem. It's the exponent that I need to get a 1. And that's because of the way Euler's theorem was phrased in general, is that 120 is the Euler phi function of 143. So 143 was the modulus that I decided to use in the very first place. And after that, that led immediately to the number 120 being part of the game, because 120 is Euler phi of 143. And that number now shows up in 2 contexts. One is it's the number of candidates that I have for this number A. And second is it's going to be the exponent that I use on that number. Whatever your base is, if you raise it to the 120th power, you'll always get something congruent to 1. So that's what I'm using now. It's not so much that I want to get a 1 coming back. What I want to have coming back is the original number at the base that I had in there. I wanted to get, it's not so much alpha to the 0 power that's of interest to me. That's Euler's theorem. But it's this next step that's actually better for me, for my purposes. You'll see in a second. It's going to be these, as long as these exponents are 1 more than a multiple of 120, I'm going to get back the number that I started with. That's what decryption means. It means getting back what you started with. So let me just do, I'll do some calculations for you, and then I'll put them into practice, and you'll see why this is the thing that works. So really what I really need, I have all this stuff in quotes, but precisely now what I need is that I want 7 times E to be congruent to 1 modulo 120. It's a congruential relationship again, but unlike every other one that I've written down so far, all of those were congruences that I was performing modulo 143. This one now is calculated modulo 120. And for that, it's kind of useful that I chose this number 7 to not have any factors in common with 123, because that means that 7 does have an inverse modulo 120. Now I have to stop and think about it for a second, or I can reach for my machine.
It's 103, I guess.
Shh, don't go so fast. Well, I'm about to go fast, who am I kidding? I'm going to use the machine to do the calculations for me. I mean, what I want the machine to calculate a number that's going to be the inverse of 7 modulo 120, and as he just said, it's 103. 103 times 120. Is that, yes, wait. Oh, no, I'm sorry, I did the wrong thing. Why did I do that? 103 times 7 is obviously one more than it's one more than a multiple of 120. It's one more than 6 times 120. So the number 103 now works as an exponent that I can use to kind of undo an exponentiation to the 7th power. So let me start writing stuff out for you again. Take this off. There we go. So
would this not have worked if we had chosen a different exponent instead of 7 at the beginning? Had we chosen a factor of 120, would it not have worked?
Right, you would have had a problem if you had chosen any number to replace the 7 that had any common factors with the 120. So I deliberately had to skip over any number that was a multiple of 2, 3, or 5. So 7 was actually the smallest exponent that I could have used. In fact, you already saw that. Where did it go? We already had the situation that we found already 3 different things, which when you raise them to the 6th power, they all just gave a 1, right? So if I ask you, oh, hey, gee, I just took a number and I raised it to the 6th power and I got 1, can you tell me what the alpha was? The answer is no. You can't answer the question of what the alpha was because there's at least 3, actually there's a total of 6 different numbers whose 6th power comes out to be a 1. And that's, again, it is exactly because the number 6 has common factors with the number 120. But I knew that in advance, that's why I chose the number 7. And now that we have found this number 103, so here's my claim. The function that takes every input gamma and raises it to the 103rd power, this function decrypts. In other words, if you, here's the proof of the claim. If you take one of those numbers from one of those 120 invertible congruence classes, modulo 143, so for all alphas that are in this set, the encryption told me to replace that alpha by the number gamma, which is computed as alpha to the 7th power. Now I'm asking you to take this function f and use it to try to decrypt. Well, you're actually going to be taking the 7th power of alpha and applying this decryption function to that. And so it'll take alpha to the 7th power and raise that to the 103rd power. But your laws of exponents make that alpha to the 721. And that, of course, is, well, I'll write it out longhand. It's alpha to the 120th to the 6th times alpha to the 1st. Those are the laws of exponents. But by Euler's theorem, this much is just congruent to 1, and that part is congruent to alpha, of course. And so you have recovered the original alpha. You took this thing, you started with a letter, or I started with a letter alpha. I encrypted it by writing alpha to the 7th instead. My correspondent then can take the encrypted form and get back the original letter by raising that to the 103rd power. Of course, all the calculations have to be done modulo 143. So let me go back to the little computer session that I had going. So let's take this encrypted message that shows up over here and see what would happen if I was the receiver of this encrypted message. My job would then be to say, well, how am I going to decrypt this? And so what I will try to do is, well, I'll make a new thing that's called decryption. a new sequence. It's called decryption. And I'll form it in the same way. I'll take the sequence of all these, 103rd powers of all the gammas. Oh, sorry, not big numbers. I just want to reduce them modulo 143. And I'll do that for every gamma in this sequence of encrypted symbols. Oops. Okay, can I just not call it gamma then? I don't know what it's talking about.
Could you share your screen?
Oh, I'm sorry. I thought I did. I clicked on something wrong. I don't know what it was. There we go. Is it? Did you get it now?
Yeah, now it's visible.
Sorry, I don't know what I clicked wrong. Anyway, I can see why. I think I know why Maple was objecting. That sequence of letters, G-A-M-M-A, I think it uses that to refer to there's a specific number, which, by the way, was also first encountered by Euler, and it's called Euler's gamma, and it's a famous conjecture that it is an irrational number, but nobody knows for sure. Anyway, here's what happens to the person who receives the encrypted message. They take this encrypted bunch of symbols, raises each one of them to the 103rd power modulo 143, and look what they get. They get 15, 1, 23, 8, 142, which is exactly the same as the message that I started with. So if that person sits down with the little table that I had given originally, let's stop sharing and pull up the table. Now that person can just read character by character and say, oh, I see, the first thing that was in the message was the number 15, that stands for the letter M. And the second thing was the number 1, that stands for the letter A. And so on, they just go through this little table, and they can decrypt it character by character, and they see that, oh, the message was M-A-T-H space, and so on down the chain. And so they discover what my original message was. So the point of this little exhibit that I just did for you is to show how the encryption and decryption methods work. And the reason that I mentioned it at this part in the course is that obviously I did all of this by using some raising of numbers to powers. And along the way, I did have to know a few things. I had to know Euler's theorem, which guaranteed for me something about coming back to the number 1. And I did have to know also which are the elements that I could encrypt, that I could only use the invertible congruence classes mod 143, which required me to have a large number of, I needed the Euler phi function to be something fairly large. Now, what makes this a good encryption thing? Why do people bother using this instead of some other? I mean, realistically, there's ancient substitution ciphers that people have used in the past. I could have just written out a random table here, and then in order to decrypt it, somebody would have to get their hands on the table. And if I and the recipient of my message are the only people that have this table, well, then the system is secure. So, I mean, until today, if I had just started to write you guys out a message that began with 15, 1, 23, 8, 142, you wouldn't know what to do with it, of course, and so it would be a completely mysterious message. However, the encryption method that I have just presented to you guys does not depend on this table being secret. I can tell everyone in the universe that all of my encrypted messages will use exactly this encryption system. I can just advertise that I'm going to use this. It's basically the ASCII encoding system, except I had to skip over a few things. So there's nothing in my secrecy method that requires having, that requires me keeping this table secret. All right, well then, you could say, okay, I guess a part of the secrecy is that I did go through the next step of encrypting. And in order to do that, what I did was I raised everything to the 7th power. And as you saw, that gave some fairly mysterious rearrangements. This number 15, when he raised it to the 7th power, I don't even remember what that came out to be. That was 115. So even if people knew that I was going to take exactly that substitution table, when they saw the 115, I mean, I guess they would start scanning this and get to the 115th character, and it wouldn't have made any sense. But here's the thing. I can even make this perfectly public. I can tell everybody in the universe that this is exactly how I'm going to encrypt all of my messages. In fact, I can make this not only public sort of by accident, but I can advertise this on my personal website and say, if you want to send me any encrypted messages, use exactly this substitution technique to turn things into numbers, and then use exactly this encryption thing to make the messages secret. Well, that doesn't sound very secret. If everybody knows how the method is for the encryption, then all they have to do to decrypt is to go through exactly what we just did down here. I mean, I was assuming that the person who got my message was going to be able to decrypt. And as you saw, the only thing that they needed to do was to be able to take the 7 that I made perfectly public to everybody and to find an inverse of it modulo 120. And, well, if I've told everybody that I'm going to be not just using the 7th power, but doing all of my calculations mod 143, then there's nothing secret about this. And the only thing secret about this is that it's the Euler phi function of 143. So if you know that I'm working mod 143, all you have to do is compute the Euler phi function of that. Here's the one catch. In order to calculate this Euler phi function, the first step of this is you have to be able to factor this as 13 times 11. You have to be able to take that modulus, even though it's made perfectly public, and even though this exponent is made perfectly public. The one thing that I don't make perfectly public is the factorization of it. If I sent you guys this secret message, I would assume that you guys could factor the number 143. In fact, so could any eavesdropper, but that's because the number 143 is fairly small and it's easy to factor. If you don't know how to factor the number 143, then you don't know how to calculate the Euler phi function, which means that you don't know how to get this number 120. And if you can't get that number, then you can't get this number either. So in order for me to make this encryption method work, what I have to do is to make the 143, or whatever I'm going to use instead, I'll make that number public. I can make this number public. And to the recipient of my message, I can make the factors public, or not public, but just I could whisper to them what the 2 factors are. But to everybody else, they'll have all of the ingredients except for that factorization. And without that factorization, then there doesn't seem to be a way to compute that the inverse of 7, something that will work just like a 1/7 in an exponent. And that then becomes the essence of the security of this system. It's all based on the difficulty of factoring the modulus that you use. So I will let you guys look this up further if you're interested in. It's known as public key cryptography. And specifically, the method that I've just presented is what's known here as the RSA algorithm. And I do want to emphasize that the encoding method is made public, and the modulus is made public. So this was the table that I gave you with the 120 entries. This was the number n, which I used 143. And also the exponent that I used, that could also be made public. That was the 7. The part that's kept secret is just the factorization of n. Because anybody who gets the factorization, well, let's say anybody who took a number theory class like you guys, after you get the factorization, you can compute the Euler phi function of it, and then you can compute inverses modulo that number. So it's the whole security of the system just rests on the fact that factorization is a hard thing to do. Hey, perfect. I actually got the whole algorithm described in 50 minutes. Go ahead, your question?
So how does the recipient know the factorization of n? How
Well,
do we send that message?
that's a good question. So that's the part that's often done by a secret courier or something like that. But in practice, the way this is done is as follows. In order to send a secret message, it's the person who is going to receive the secret message that gets the factorization in the first place. And the way that they do that is they get some large prime numbers at random. They generate some big numbers at random and test them for primality. And if the numbers that they got were not prime, they just pick another number. And you just keep doing that over and over until you've gotten some big prime numbers. Those take the place of the 11 and the 13. They multiply those two big prime numbers together and they can now publish the product. They are keeping the two primes that they have discovered on their own. So again, let me say that it's the recipient of the message who usually generates the number n as a product of two large prime numbers. And then they can make the n, the product, public along with the exponent and of course the initial table. So I could do that, for example, and then anybody who wants to send me a secret message, I would have my personal pair of primes, okay? So the value of this, the way that this encryption method tends to work in practice, unless you have a secret courier to transmit the P and the Q, is it's the recipient who advertises, I would like to receive a secret message. Here's how to encrypt it. Don't worry about the decryption. I'll take care of that.
That makes more sense. Thank you. And about this gamma constant, is it related to the gamma function?
Oh, no. So the Euler gamma, it's defined to be the limit. I may have it, it's this way or the reverse. It's, you know from calculus that if you take the sum of the reciprocals of the first few integers, then this is approximately equal to the natural log of n, of k rather. But they're not, they get closer and closer in the sense of their ratio gets closer and closer. The difference doesn't go to 0. The difference goes to some number, and I think it's like 1.6 or something like that. But anyway, it's something that you can calculate. It's just nobody knows whether it's a rational number or not. Hang on, let me see if.
So Euler has two constants named after him. Is he the only one, or are there other mathematicians who have several constants with their name?
That's a good question. I don't know the answer to that question. By the way, I just looked this up. It's 0.577. I don't know what I was thinking about here. You're right. So yeah, Euler's, there's also Euler's E. That's 2.71828. I don't know. Another mathematician with two constants. I guess I can't think of one. Sorry. That's a good question. It's a funny question.
Thank you.
Other questions? All righty, guys. I'll see you again on Friday.
See you on Friday.
Actually, I had one quick question, if you don't mind.
Oh, yes, you caught me just in time. I was about to end it.
This is a unique mapping, correct? Like, for every input, you have exactly one output. So if it were just letters in English, theoretically, you could still use the standard cracking that they used where they like, no E is the most common letter and so on?
Yes. Yes. Oh, well, there's all kinds of things that you could use if this were, the way I just did it, where you're going letter by letter, that's horrible in terms of what you just said. I mean, it has other deficiencies too, like you notice that the letter A is never encrypted. And so right away, because 1 to the 7th power is 1, so some of the letters didn't get encrypted at all. And what you just talked about was what's called the frequency analysis. Since the letter E is the most commonly used letter in the English language, when you see a very long string that's just as a translation of one letter at a time, well, you just look for whichever character shows up most often, and then that is assumed to be the encryption of the letter E.
So it would just take like chunks of bits instead and just
correct.
pure
So that,
machine code.
yeah, I said earlier, if you just took 4 letters at a time, already you're looking at strings of 28 bits. and that's got a lot less predictability to it. And as I said, the usual choice, what's considered a fairly secure choice, is to use a modulus n, which is about 1,000 bits long. And so you could have a pretty sparse embedding of strings of dozens of characters at a time into that set of allowable characters. So yeah, you can pretty well defeat the frequency analysis.
All right, cool. Just want to make sure it was unique, because if it wasn't, that left some real problems to
No,
decrypt.
you're absolutely correct. No, and there's all kinds of other things that, I'm assuming when I say that this is secure, I'm assuming that people don't know how to factor an integer. Well, it's not, nobody knows a way that can guarantee to factor just any old big integer, but if you aren't careful about choosing those primes P and Q, then it turns out that there are ways that you might be able to factor that kind of integer, So there's a lot of potential deficiencies in this system, but at least it's impervious to some fairly straightforward attacks.
Makes sense. All right, thanks.
All righty, thanks.
I have one more question.
Yeah, go ahead.
So I think I missed the class, but we kind of discussed about the tests and everything. The test will be next week on Wednesday, correct?
I don't think we said it was going to be on Wednesday. I thought I was going to make it the next week on the Friday.
Okay, my bad. I didn't know. I just based it on the calendar, what I saw, and I thought it would be Wednesday because it's just by order.
That's a good question. I think I know what you're referring to. Were you just looking at this?
Yeah, I'm looking at that.
No, but you see the way I have it, I don't know if you can see it on my screen. Yes, it's the second entry in that list, but it's also the last entry in the list. So I was thinking that would mean that it was on the Friday.
Okay, so since it's on a Friday, based on what I remember reading, it's basically we take the test, we download the test as a take-home kind of test, and we have a day to complete it, and then we sign up for office hours later to discuss the test with you and go over the answers.
Yes, that's my intent. We're going to have to talk about it. Actually, I'm glad you said something just today, because we will have to discuss this on Friday to clarify that this is what people want to do. You have to realize we're making this up as we go along the semester, right? Everything is, nobody really knows what they're doing. But let's talk about it on Friday, okay? I'll make it a point to talk to the class to see what they want to do about the test.
Okay, sounds good. Thank you.
Okay.